Check, check. All right. Hello. Hello, everybody. We're ready to get this show on the road. How's everybody doing tonight? There's a lot of rain. It looks like the rain has stopped a couple people, which is very understandable. I hate driving in the rain, especially in San Antonio. Anyways, first-timers tonight? Anybody? Cool. Yeah. Welcome.
Woo!
Soon. Yeah, so this is Astronomy on Tap. My name's Aaron. Michael over there, Sam over here. Brian and Adam running the show, keeping everything going. We got Thomas online, checking the streams and whatnot. And then the OG Tracy Becker is taking care of her family with her husband, and so she's not here tonight. I think that's everybody. Oh, Erica, I'm so sorry. We have Erica as well. Yeah, so for those that are new, Michael, what's AOT?
Well, first of all, welcome to the first post-eclipse AOT. How was the eclipse, everyone? Yeah? I know, the weather today is fitting because, the clouds, we can't control that, but at least it got dark, and it got really dark, so I hope everybody got to experience that. Not until March we won't have another lunar eclipse, which some people aren't big on that, but they're exciting. So that was a great time, and I hope everybody got to enjoy it. And now you won't hear us talk about one until the lunar eclipse. So we're done bothering you. But we're not done bothering you about us. Who are we? We're a worldwide phenomenon. We have locations across the globe. It started over 10 years ago now in Brooklyn, New York. And as you can see, it's expanded. Our own location started in 2017. So we're going on 7 years now here in San Antonio. So this is event number 43. And that's not including the COVID online events that we had in the interim. So it's a little bit about Astronomy on Tap in general. Us here in San Antonio, well, we like to have fun. Hopefully everybody tonight enjoys the talks and has a good time. We like to keep them interesting. As you can see tonight, we have a range of talks from exoplanets to anime. So, I don't think it can get any more interesting than that. That speaks for itself. Interactive, you all will get to ask questions at the end. I'm trying to get the television working, but there'll be a number you can text for that. And lastly, a chance to win, because we always have trivia to close out the night. So pay attention, but at the same time, Sam has been doing a good job making the trivia questions kind of open for all. But as always, astronomy related. We made sure that they were all astronomy related. So good job on that, your trivia questions. I noted, they're on topic, I'll put it that way. Please follow us on our socials if you don't already. We keep, every month we'll post about our upcoming events, and sometimes we'll post some interesting things NASA has in the interim. And that's all about us. So now here's Sam for our schedule for tonight.
Test. Okay. Real quick, please send us any eclipse photos that you did take. We can put them up here during break times and credit you accordingly. So our schedule today, Dr. Amílcar Torres-Quijano is presenting on this. I'm not going to say all of that. He will say it. Then we'll have a 10-minute break where Caleb will give astronomy in the news as usual, followed by Dr. Roman Gomez's Physics of Anime Abridged. I don't know what that word means.
It means you don't get the full thing.
Okay. I looked through it. It looks really cool. So that's all I have. Thank you.
All right, as mentioned, our first speaker tonight is Dr. Amílcar Rafael Torres-Quijano, who is from San Juan, Puerto Rico. Woo! He earned his Bachelor of Science in Physics from the Universidad de Puerto Rico Recinto de Rio Piedras, or UPRRP, yay acronyms. He then worked as a software developer for General Motors and as a mathematics and science tutor for students of all ages. Since then, he has obtained a master's degree and doctoral degree in physics and astronomy from the University of Texas at San Antonio. Go Runners. His future endeavors include securing a postdoctoral position in small planet research, fostering astrophysics education in Puerto Rico, and starting a mental health awareness group for those in academia. So without any further ado, Dr. Torres-Quijano. All right, let me get the phone. So before we start, most everybody in here is a regular, so you know about our drinking word, but I'll give a quick reminder. Amílcar will say a word during his presentation, and we will all give a woo, hold your drink up and go woo. So what's today's word?
It'll be, hello? No?
Push the button.
There we go. It'll be features.
All right, everybody gets it. All right, so go ahead. Oh, yeah. Down to advance, and there's a laser down there.
Fun times. Alrighty. Hello, everyone. Hopefully, everyone's doing well. So, specifically, I'll be talking about using machine learning to predict host stars and the key elemental abundances of small planets. Basically, we want to see which elements will let us know if there's going to be a planet or not around a specific star. And before I start, this research project that led to my dissertation, these are all the co-authors here. Natalie Henkel, Caleb Wheeler, Patrick Young, Luan Gessi, and Augusto. And then, of course, throughout the talk, you'll be seeing a lot of video game references, because this is what led me to astrophysics, basically. This is Star Fox. If you're not familiar with the game, you should play it. Alrighty. Then about me, so like it was mentioned, I'm from San Juan, Puerto Rico, that little star there. That's approximately where I'm from. The slide is a little bit cut off, but this is 1 year before the Arecibo Observatory collapsed. I was just starting my program here at UTSA. I was also a Super Smash Bros. Caster 9 years ago, which is unfortunately no longer a thing, but it would be fun to come back to. And then I play a lot of D&D, so roll for initiative there. These are two of the characters I've played as. I've played way more than that, though. And then that's also my sister's art, so I had a chance to kind of show it off. Alrighty, so in order to basically understand that, how to find those elemental abundances that might tell us if a planet or not will form around a host star or will be present, we also need to understand how stars and planets are formed. And in essence, they form from the gravitational collapse of a molecular cloud core, basically from that same material. And then the remaining material that is going to be there is a rotating disk of gas and dust, and that will surround the young star. So here in the center, this is a protoplanetary disk. The young star would be there, and then you would have that material that remains. And then that material can accrete and form larger objects. At start, it'll make small dust grains, and they'll start joining up together and accreting to larger objects, protoplanets. And then some of the elements that are important for that are carbon, oxygen, magnesium, silicon, and iron, which can condense to form those interiors of rocky planets or small planets, things like that. You'll be hearing me talk about those elements a lot, by the way. And then, of course, here, this is image, like I mentioned, is a protoplanetary disk. You can see these gaps. It's been thought and studied a lot that those gaps might actually contain planets that are in formation at the moment. So, more on that star-planet link on that background. Stars and their orbiting planets, again, form from that same molecular cloud core. So what we want to find out is, are there any specific elements, combination of elements, that will let us know if a star will have a planet or not? And then we have already seen that that relationship has already been established with iron, but specifically for giant exoplanets. So things like Jupiter and Saturn. So again, iron is commonly used as a proxy as well for a star's metallicity, But there are other elements that are very important for that. Again, carbon, oxygen, magnesium, silicon, and iron. In different ways, which we'll see how that affects us later. And then the combinations of those elements can make minerals that are important, are a primary component of the interiors of planets. So for example, in Earth, we have things like olivine, which make up parts of its upper mantle. So again, with those elements, you can make the bulk composition of Earth, or Earth's internal composition. You have carbon and oxygen also being important for bonding. And another thing that we wanted to look at is the molar ratios, or otherwise those ratios between two elements, iron and magnesium. Can they influence and let us know more about small planets in some way? So iron to magnesium, it's been shown that it can influence the size of a planetary core. Silicon to magnesium, it can affect the proportions of olivine and pyroxene in the mantle. And it can also let us know how these olivine and pyroxenes, etc., are distributed through a protoplanetary disk as well, which we'll see a little bit further forward. And then, of course, since you have that indirect link of these elements and the star's abundance, then we can potentially use it as a proxy to study small planet composition, giant planet composition as well, but we're focusing on small planets compositions there. So, now that I talked about molar ratios and the elements, these will be the features that we'll be looking at once we'll be starting this discussion of the study. And we had some questions going from there. So if we separate the small planets, and we'll define what these are in a second, if we separate these small planets into different groups, will we see certain elements having more importance in determining the presence of an exoplanet? And what is the effect of iron and volatiles on the importance of specific elements? And then do those molar ratios give us more insight? And then, of course, I looked up for the proxy system here, the LILAT system. It doesn't exist, by the way, but we have it there as an example. So again, that motivation. We want to understand those three key factors when dealing with small planets. Is there a general stellar composition that'll indicate the presence of those small planets? Can we predict which stars have a high likelihood of hosting those planets? And can we further constrain formation processes? So now that we have all the questions, we have to figure out, okay, how are we going to go about this, specifically because there's going to be a lot of data. So this particular study builds upon Hinkle et al. 2019, which did a similar thing, but instead of looking at small planets, they looked at giant planets. And they used an algorithm called XGBoost. Basically, it's just a machine learning algorithm. To determine the elements that would be important and the abundances of the elements that are important in highlighting the presence of those planets, in order to also demonstrate that the algorithm is really good at doing this job. So here, they determined, which we will also be determining, what the feature importances are those elements or molar ratios, and then the elemental abundances of the host stars. And one of the cool things that we could do was also produce a list of those stars that will have a 90% chance or greater of hosting those small planets. So essentially, it allowed us to build a potential target list that observers can use to find small planets later on in the future. And then this little guy is Watt. He's a little star buddy here from Paper Mario. It's pretty cool. I don't remember him being that important in my playthrough, but you know, needed a star to kind of like have it there. So let's begin here with the data. So where did we get that data? So here gets a little bit more number crunchy, but essentially two main points of where we got the data. First, the stellar abundances, or the elemental abundances of a star, was taken from the Hypatia catalog, and then the small planet data was taken from the NASA Exoplanet Archive. In the Hypatia catalog, there's around 11,000 stars. These are FGK-M-type stars within 500 parsecs from the sun. In other words, they're relatively close to the sun, and around 1,500 host planets. And then for the NASA Exoplanet Archive, we actually, I believe it was in March, end of March, we finally hit over 5,600 confirmed exoplanets, so that's super exciting. And then this graph basically just shows you how the detections on exoplanets have increased over time since 1992 specifically. And we see, for our case that we're looking at small planets, transits is what's going to be important. It's where our data primarily comes from, and that's the larger part here. other side. All right, the data. So now that we have the abundances and the exoplanet data, we combine them via the stellar ID. Basically, every star has a name, and we just combine those two via that star's name, and then we have a full overview of the system, where we have the elements of the star and their abundances, and then any planets that it might have. And then from there, we can then define which features we want to test on. Those features, of course, being the elements or molar ratios, which we'll look a bit on the whole list in a second. And of course, it's a lot of data, so many numbers. All right, so now that we have the data, now we need the algorithm, so the code that we have to use. So the best example that I can use here is we've all used services like Netflix, right? So essentially, it's a supervised classifier similar to what Netflix uses. And what it does, Netflix basically provides you movie suggestions based on previously watched material, right? So the way it does that is the algorithm on the back end of Netflix is basically being trained by those movies or shows that you watch or the likes that you give it, essentially. And once that is trained, the algorithm then goes, okay, I know what this person likes, I know the patterns that are there, so with those patterns, I can apply them to the catalog of movies that I have here on Netflix, and then I can give the user suggestions based on that, on what to watch. So for us, similar, but now instead of movies, we're just looking at stellar abundances and planets, right? So this is Rob64. I don't know why he came all the way up to the classifier there. He was supposed to be under here, but cool. Anyways, so for our case, we build a relationship between, so for our available data, so the training sample, which in our case is, which systems have exoplanets? Okay, that'll be our training sample. And then the prediction sample will then be, which systems do not have planets, or do not know that they have planets? And then from there, it'll make those patterns, it'll trace those patterns basically with the code, and then perform predictions to tell us which features are the most important, and then which stars then are predicted as potentially hosting a small planet there. Cool, now that we have the algorithm, we can finally start setting up the project itself. So I talked a lot about small planets. What are they? So essentially, those are planets that have a radius less than 3.5 Earth radii, basically. Or if you take the radius of Earth, 3.5 times larger than that and below, that will be our experiment 1. Basically, we'll test on that whole group. And then we subdivide that into 2 more. So the planets between 2 to 3.5 Earth radii, those will be our sub-Neptunes. And those that are 1 to 2 Earth radii will be our super-Earths. Now, unfortunately, we could not test anything smaller than this because we didn't have enough data, but it's definitely something I wanted to look into the future. And then every single experiment there is also subdivided into ensembles, or better yet, groups, where we tested different combinations of features. That being, there you go, combination of elements, adding iron and volatiles, or combination of molar ratios. And then these are all the elements that we test on here. So our volatiles would be carbon and oxygen, lithophiles would be this group here, and then siderophiles, this group here. I could list them all, but it would take a while. So from there, we can also make what we call the overlap stars. Here we have 2 overlapping stars, although now that I think about it, it'll just make the sun invulnerable, and I don't know if that's a good thing. So essentially, remember how I said we would look into the stars and the algorithm would tell us which stars had a 90% chance or greater of hosting a small planet, right? So what we found is that if we take the stars that for each group or each test basically are repeated, we can see the same star, then we can say, okay, that star more than likely has a planet in our group. And then for each experiment, we can then have a list with potential targets. So for the small planets, so that group of 3.5 Earth radii and below, that's 96 stars, 94 for the sub-Neptunes, and 358 for the super-Earths. This is a good question. Why is this one larger? I could talk about that, but it would be a good question to ask, of course. But essentially, it has to do with how the code works and how it looks at data, specifically data that doesn't have values in it for the abundances of a specific element. And then once we have that data, those stars, that'll allowed us to basically plot the abundance values of the shared stars and help us infer maybe any properties of planetary interiors. So, with all that in mind, now we know how the code works, what it can produce, the observation target lists, what did we actually find going from there? So we found that sodium was the most important element in determining the presence of a small planet. I mean, I don't know. Anyways, I guess in that sense, we weren't expecting sodium. You would have, if you know anything about small planets, you would expect to see something like those elements that we talked about initially, magnesium, silicon, iron being the most important, but that wasn't the case, it was sodium. So we had to ask ourselves why that is. It was actually a very interesting talk. We had to talk to geologists, Dr. Speck and Dr. Whittington as well. Dr. Speck, not a geologist, her husband is, but anyways, point being, we wanted to see why it was so salty. So basically what we saw is, so it's the most important element, but when we look at planets, there's a lack of moderately volatile elements. So people have hypothesized that this depletion could be during the formation of a small planet, or the outgassing during formation phases as well, the magma ocean phase. Just imagine a planet all lava. If you've seen Mustafar in basically Star Wars, that's it. That's a magma ocean phase. So outgassing of sodium there, or moderately volatile elements. I'm going to call them MVEs, by the way, from now on, because that's a lot. And then, but still, if you look at the crust of certain solar system bodies, it's still kind of common. You see it in the form of plagioclase in the Earth, Moon, and Mars. And then we also were able to plot the sodium abundances versus the iron abundances. And what we noticed was that, this mic is weird, we noticed that the sodium abundances were subsolar, so they were much lower than the prediction sample that did not have planets. So anything that was predicting having a small planet, or the systems that we already knew had planets, the sodium abundances for those stars were actually lower than the rest of the sample. And then at the same time, them being distinct, it could also potentially hint at upper limits where sodium might be preventing or hindering formation. But it could also be limits in detection, because of course I mentioned transits at the start, and there's a lot of biases during that method of observation. This is another element that we saw, the second most important abundance. It was vanadium. How many of you know a lot about vanadium? Yeah, so same reaction here. I had no idea what vanadium and why it was important in the formation of planets, or in determining the presence of a planet. So what we initially thought, that should say tracer, not trace, but that's the point. So for this, it was the second most important feature. So what we thought about was, okay, it might be likely due to its role as a trace element. So basically what that means, it's letting us know what the formation processes that are going on in a small planet. And this has been shown to be, for vanadium specifically, for mantle melting and for the formation of planetary cores. But the most interesting one was also that it can have various valence states. So that means looking at the electrons and how many electrons are missing for terrestrial planets. So it could also be letting us know what sort of redox processes are happening in the core or during formation of a rocky planet. Now I mentioned molar ratios. I'm not forgetting them. So which are the important molar ratios in determining the presence of a small planet? So we had 3 different groups, and what we did is each group had a different element on the bottom. So here, and by bottom I mean so magnesium, so element over magnesium. That was that group. And then for that specific group, what we saw, so we couldn't really tell, so remember that giant planet and iron significance? We couldn't really say that for small planets, but when looking at the molar ratio, specifically iron to magnesium, was the first or second most important feature for that group. And then what that means is that this might be hinting at you need specific Fe to Mg, or iron to magnesium ratios, in a specific host star for the formation of planetary cores. Likewise, magnesium to silicon was another, silicon, I should say, was another group of molar ratios that we tested, group 6 specifically. And in experiment 1 and 3, or for the small planets and the super Earths, what we basically saw, it was the most important. And this element, as I mentioned at the start, it allows us to understand how that distribution of magnesium and silicon are in a protoplanetary disk. So what we saw when we looked at the actual numbers there for the groups is that the magnesium to silicon ratios were suggesting systems where the silicas are distributed between olivines and pyroxenes during that formation phase of protoplanetary disk. Only one particular star had a ratio that did not satisfy that, but if the beginning of the range was 0.86, that star was 0.85. So yeah, so even though it fell out, it was still very close to that range. Oh, I should mention, so I didn't mention sub-Neptunes. Sub-Neptunes actually had calcium to silicon being the most important. And that one was a cool ratio because, so what we saw is that there's some papers that are talking about how calcium and silicon might be important in determining the low densities of certain classes of super Earths and certain classes of planets, specifically those where their cores are not solid. It's diffuse. And one of those planets is 55 Cancri E, which is a magma ocean world, like I mentioned before. And so that is an interesting difference, at least, that we saw between these 3 groups that we tested. Oh, there we go. And then magnesium, so with respect to oxygen was our other group. And what we saw is magnesium to oxygen was the most important. And then, so the interesting thing about this particular ratio is that it could potentially tell us where these objects are forming, either exoplanet, exomoon, asteroids, and this has been shown with respect to white dwarf pollutants. So white dwarfs, basically a star, low mass stars after it dies, and then the pollutant being one of these objects basically falling into that star and staying in the atmosphere, essentially, the material. And then you can study what that atmosphere and those elements are, because it's not what you would expect in a white dwarf specifically. So if you see anything else, those pollutants are probably coming in from a pollutant like that. So what they found is that magnesium to oxygen basically could tell us that what is the certain distance they are forming from that particular white dwarf. So it's basically, after a star has died, it is still giving us information on how the system itself formed trillions of years ago, or billions of years ago, I should say. And then, so essentially this leads us to our basically final idea is, can we find a planet recipe? And by planet recipe, what I mean is, what sort of elements, what sort of abundances are necessary to basically start that formation of small planets. And so one of the things we saw is that those abundances were actually kind of constrained in a specific range. So if we are able to get that range a little bit more precise, we could potentially be able to detect small planets by targeting stars with specific stellar abundances. So we know the stellar abundances that we were looking for, so if we just find a star like that, then we'll probably find a planet around it. And then it also might imply what the specific abundances are required for the different sets of planets that we were looking at. And of course, the cool thing, which not specifically one of the things that we set out to do, but after we looked at the molar ratios, we saw that we could, is it could allow us to determine, we look at a protoplanetary disk, so while these planets are actually forming, and we can tell if they're gonna form a small planet or not based on those abundances. So in summary, we tested a bunch of different planet groups, divided into different groups as well, ensembles, to test the important features. We found that sodium and vanadium are the important features, regardless of radii. We created a list of stars that have a greater than or equal to 90% chance of hosting small planets, which could be useful for future missions in terms of selecting targets and finding planets, of course. This is p-value, didn't talk about it because it was very mathy and very statistics based, but if you have any questions about that, I can answer that. But essentially, with these two studies, we're very confident that these stars will host small planets and will be useful in these future missions. Or, well, JWST is not a future mission, but these two. And with that in mind, we made it. Slippy Toad here would say. Do you have any questions? I'm also on the job market. This is my website, CV, etc., through the QR code. Thank you very much.
Thank you so much, Amílcar. Aaron's going to put my number on the screen here, so you can, and it's a small screen there for those that can't see it, but I'm trying to get the television working. It's being finicky right now. My first question is, what is redox? You talked about, what is that?
So redox has to do, those interior processes that have to do with basically oxygen going on in the system. But that's pretty much the extent of vanadium and what we looked at. So that is the general answer. We were more focused on what the importance of that element would be in terms of tracing those processes.
Okay, thank you. I don't know much about vanadium, but I've always known that I like it because it's V. So, you know, V for Velas.
That makes sense.
Let's see here. Is there an observational bias in elemental abundance and location in the galaxy? For example, are there higher abundances of an element closer to the galactic center versus farther out?
So we specifically looked at stars within 500 parsecs of the sun. But that's one of the things that we mentioned in the paper is actually the biases specifically due to, one, that distance, but also the observation method. Because 91%-ish of the planets in our data set, they're all from Kepler K2. And since this uses transits, these are more basically biased towards larger radius planets that are also at shorter periods, because it'll affect more of that starlight that's being dipped. So that's one of the things that we also make sure to point out that, hey, there might be biases in the abundances for these specific planets based on the data that we're receiving because of the transit method. But one of the going back to the galactic bulge, as we get more stellar abundances from different locations in the galaxy and of different stars as well, we would like more M-dwarf abundances, please, by the way. We would be able to test more specific cases and actually get a further confirmation if there's going to be differences depending on the location of the disk.
Okay.
A star's location.
Thank you. If you had limited funding and 10 years of time, what would you change in this project?
Unlimited funding.
Unlimited.
Unlimited, sorry. Unlimited.
Because my original question was going to be how limited, but I guess if unlimited, then. So I mentioned how I would like M-dwarf stellar abundances. So probably first getting a project that would get a lot more abundances. That my advisor is actually working on one. So hopefully that goes soon. But anything to supplement that, because if we have those M-stellar abundances, then we can test smaller radius planets, I should say. So anything under 1, for example. And then the large number that you saw for the small planets that said, oh, we have 358 for the overlaps, right, when compared to the other ones where we only had 90. The reason was because we used those null values. And the way the code works is that if you have an empty elemental abundance, the code goes, probably a planet. I don't have an abundance value, so that probably means there's a planet there. So what we could do if we have those abundances is remove the necessity of the null values for that particular experiment. Because we were able to do it for the other two, but not for experiment 3, which is the superhertz. So that would be the primary thing. The second would be actually trying to observe the stars that actually are in the 90% chance or greater, to see if we could confirm, we tested this, the code is predicting this will have a small planet, Now let's observe and see if we can actually find them. And that would be really good for, that would feel really great to have those observations and confirming that.
Did you validate against existing exoplanet detections or just predict undiscovered exoplanets?
Very good question. So, yes. So the way we actually made sure the code was working was by validating with systems that actually already we knew had planets, right? We called that the golden set. Actually, can I have I actually have backup slides for that particular thing. Let's go. This is like the more mathy stuff. There we go, the golden set. So what we did is we extracted basically a group of 10 stars every time we had an iteration in the code. And then we told the code, hey, interpret these stars that we know have planets as if they didn't have, as if we don't know they had planets or not. And then what we did, we just had the code run and made it predict on those stars. And what we found through thousands of iterations of the code, we're talking, so every run of the code is done 25 times. That is then done 3,000 times in each 25 run, so thousands. And what we found is the code, when it was predicting the systems that actually had, that already we knew had planets, had an overall score of around 84% for predicting those hosts. And with that, we knew, okay, the code is working really well. For context, that's around a 5% increase of my advisor's paper in 2019, where we had less data. So just with that, you can see how having more data actually even improves also the efficiency of the code as well, having those abundances.
Very cool, thank you. For the importance of feature, based on what values are they ranked, and what was that value for the most important feature?
Right. So, it's a weighted feature importance score, but the way that score is determined is, so XGBoost works with decision trees. So what it does, it looks at the elements that you're testing on, and after looking at the elements, if that element is efficient in splitting the stars into it will have a planet or it will not have a planet, then it gives a score to that particular element. So since sodium was the most important, every time it saw sodium do that split, it would weigh it higher than the others. And then at the end, you have all those values together, and then you could basically plot them. Let's see if I have them here. There we go. So that's how it would look, essentially. The different colors basically means elements are varying between different groups. Blue means they don't move. But essentially, this is how it would look. And you would have a score that you could plot, and then you could visualize to determine which element was the most important.
Very interesting, thank you. All right, there were some more questions, but we'll have to move on. So if anybody has any more questions, you can, I'm sure Amílcar will be glad to answer them directly. Find him around. But let's thank Amílcar once again. All right. I put it back. Okay. We are on break now for 10 minutes. We'll return to action at 7:50. 7:50. Enjoy your break.
Halo Gamar, take it away.
Hello. Well, all right, let's go ahead and start with astronomy news. So there's a few rather interesting things to talk about here. First off, what is up in the skies for the month of May? Unfortunately, all of the bright planets, with the exception of Jupiter, which is starting to get very low in the evening sky right now, are for the most part in the morning time sky. So if you go out in the early morning, around about 5 to 6 in the morning, look over on the eastern horizon, you will find Saturn and Mars, and maybe, just maybe, if you look really close, the planet Mercury, all in that nice row rising over there in the east. Nonetheless, in the evening time sky, about 10 o'clock p.m., this is what you will see. It is very much the springtime sky. The constellation of Leo the Lion is almost straight overhead. Remember, you can always find the springtime constellations by looking for the very familiar pattern of stars known as the Big Dipper, right there, otherwise known as Ursa Major, the Great Bear. Follow the arc of the Dipper, and it always arcs to Arcturus, part of the constellation of Bootes, the herdsman. Follow the front two stars of the Dipper on down to Regulus, the heart of Leo the Lion, right there. Also, if you keep following that arc to Arcturus, you can spike down to Spica, which is part of the constellation of Virgo there in the sky. So it actually is fairly easy to navigate around the springtime sky, but unfortunately, you are looking in a rather barren area of the sky, as it so happens as we enter the springtime season. As we revolve around the sun throughout the year, we face different parts of our galaxy, and because of where we are in relation to the sun and the tilt of the Earth on its axis, we are facing toward the direction away from the plane of our galaxy for the most part during springtime. So when you look out that direction, there are not a lot of extremely bright stars there. Most of the stars are a little more distant. It's not as densely populated with stars and some of the star-forming gases and things like that that characterize, of course, the plane of our Milky Way galaxy there. Nonetheless, it's a great time of year to look for the galaxies. So if you have a backyard telescope and you go out under a really dark sky, get about 2 hours away from town toward a darker area, look there, right toward the tail end of Leo the Lion and just above Virgo there, and you will find a whole bunch of little glittery gray spots that kind of twinkle in and out of view. And those are many distant galaxies, an area that we call the Coma-Virgo galaxy cluster, about 70 million light years away or so. So that light left that region at the time that the dinosaurs were wandering the face of the Earth. So, some really fascinating, okay, there we go. Yeah, some really fascinating findings from the James Webb Space Telescope, just announced within the past couple days or so, actually. This exoplanet, actually, it's modeled here. That is an actual image of it per se. WASP-43b is a very large hot Jupiter, as it's called, and as it so happens, it's so close to its parent star that it is tidally locked, meaning that one side of the planet always faces that parent star. And the JWST made a series of observations which showed the weather properties in the atmosphere of this exoplanet. So here's what you're looking at here. You are seeing the light curve of this system over time. That line right there, that's basically the level of light from the star exclusively that this planet orbits around. Again, this is in the infrared band. But as the planet goes around, the very warm daytime side of the planet adds to this temperature profile. So as the planet goes behind the star, you get that little dip down when it's starlight only. And then as the planet goes around, you start seeing the nighttime side, and therefore that overall profile dips down. And then you get the very, very sharp drawdown when the planet passes in front of the star. and then back around again. So putting all this information together, you can do a little bit of math, figure out the temperatures that are involved, and you actually get a temperature profile of the daytime side and nighttime side of this hot Jupiter, where the temperatures soar in excess of 1400 Celsius on the day side and dip down below 600 Celsius on the nighttime side. These very dramatic temperature changes likely result in the winds in the atmosphere of this exoplanet exceeding 5,000 miles per hour. Really, really fascinating stuff. Now, here's something you may not have heard about. So there's obviously a series of X-ray telescopes out there in space, but there was one that was launched not terribly long ago by the Chinese Space Agency. And it's a joint mission between the Chinese Space Agency and the European Space Agency and a few of the members therein of the European Space Agency. And the first results from that X-ray telescope, are actually calibration images from that X-ray telescope, were released within the past couple of weeks. And so these are a few of these images. So this area here shows the central region of our Milky Way mapped out in the X-ray band. And then this is a detail image of the Puppis A supernova remnant from that new X-ray space telescope. Really, really fascinating imagery. Very fascinating array of missions out there observing the X-ray band. This particular one uses a very interesting imaging array. The imaging array is compared to the way a lobster eye works and the way it channels the X-ray radiation to the sensor. Definitely do some more research about this mission. It's called the Einstein probe. Very fascinating stuff, way more than what I can talk about here in detail this evening. So the Atacama Large Millimeter Array, some very interesting work using that ground-based radio telescope. Few observations of Io using this radio telescope array indicates that the moon has been volcanic for probably the vast majority of its history, several billion years. So this radio telescope was used to map out the sulfur isotope ratio in the Io system. By the way, this image of Io is from the Juno spacecraft, not too terribly old of an image there. I think it's been within the past couple of months or so. And it was able to see that basically most of the lighter isotopes of sulfur have been completely depleted from the Io system. And that indicates that much of the native sulfur from Io has been exhausted. And therefore, this has probably been going on at Io for several billion years. Not only that, that also implies that many of the dynamical properties of Jupiter's system, meaning the gravitational tugging on Io that causes that volcanism, and therefore some of the other properties of the moons there around, have also been in existence for a very long time, meaning that that liquid water ocean that may be beneath the surface of Europa, the other one of the other large moons of Jupiter, that has probably been around for a very long time as well, long enough that maybe some form of primitive life could very easily have developed during that time period at that moon. So very interesting work from the ALMA data. Finally, we have a very interesting event coming up this week. So, as many of you know, NASA a few years back moved to a different way of launching their crews into space. They decided to contract to private spacecraft providers to not only build the spacecraft, but also operate these spacecraft and do much of the support work for them. It was a new way of the space program working with a human spaceflight. Well, SpaceX was the first company to successfully work under this program to send crews into space. Boeing was the second contractor. They're now ready to do their first flight test. So these two astronauts, Butch Wilmore and Suni Williams, both very experienced astronauts, will spend a week at the International Space Station on a mission that should launch on May 6th. Now, again, that's a should launch. That could be delayed in this Boeing space capsule. It's been a little bit of a troubled program. Just let's hope it's Boeing, that everything works out fine. Nonetheless, though, I think it'll all go all right. It'll be very interesting to watch this mission unfold. So again, best of luck to that crew, and it'll be very, very neat to see finally 2 providers now in that program operating. So a few events coming up more nearby than outer space. We do have a star observing at the UTSA Observatory scheduled for this Friday, weather permitting. I'm not holding out a lot of hope that it's going to happen, but cross your fingers just for luck. We should, if the weather is clear, have a really great time observing out there. Please do indeed join us. Starts usually around sunset, just so you know. Flound Science Building, if you want more information about that, just look up UTSA Observatory online. It'll take you right to the site. And then there is an observing, amongst many of my fellow UTSA observing folks, planned for South Yona River State Park on this Saturday. Again, not holding out much hope for the weather, but if it does work out, really beautiful views out there. Strongly recommend you make your way out there at some point in time. And I will now leave you with a couple of final images. The top one here is of the Little Dumbbell Nebula. Yes, there is a big dumbbell nebula. This is not the big dumbbell nebula. This is the Little Dumbbell Nebula by the Hubble Space Telescope. This was the image that was released for the 34th anniversary of the Hubble Space Telescope, going on 34 years strong. So really, really great history that is continuing of scientific discoveries from that space observatory. And also this really beautiful image from the JWST of the Horsehead Nebula region. Of course, that's the upper part of the Horsehead Nebula. You see some of the other more wispy parts of that gas cloud, and it's that red haze there. And then all of these very distant galaxies in the background, of course, amongst the nearer stars to us there. So just a really awesome view. And that's where I will leave you, and that is Astronomy News. Thank you very much, and enjoy the rest of the evening.
Thank you, Caleb. Oh, geez. Set that there. All right. Our next speaker is Dr. Roman Gomez. He is a... no. Wait till he presents and then clap. Okay, come on. Roman is a San Antonio native and graduated from Highlands High School. Anybody?
Not many of us come from there.
He, after completing a term of service in the U.S. Army, he attended UT Austin and Southwest Texas State University. I've not heard of this place. Where is it? Oh, okay. Okay. Now Texas State University, earning a BS in physics and biology, and pursued graduate studies at Rice, and completed his graduate education with a PhD while working at Southwest Research Institute in 2011. Yeah, you can, yeah, that's okay, that's okay. He is now a lead scientist at SWRI, specializing in developing plasma instrumentation, while also an adjunct professor at Northwest Vista College and St. Mary's University, both in San Antonio. When he's not working, he frequents anime conventions like San Japan in San Antonio and Anime Expo in Los Angeles. Without further ado, what is your drinking word?
Yeah, my drinking word is going to be animation, because I think if I say anime too many times, people are going to leave with liver failure, so we're going to stay away from that. So, all right, thank you, Sam. So, yes, my name is Roman Gomez, and for one night only, you will be subjected to anime on tap, not astronomy on tap. So, normally what I work on are plasma instruments. So one that we have just delivered is SWIFO L1 SWIPS. This is a NASA-NOAA joint project. This instrument will be the solar wind monitor for it's going to launch with the IMAP mission, and from that point on, for the next 5 years, it will be the solar wind monitor. It is there to warn us when we have solar extreme events, which, as we know, can be quite catastrophic if we're not prepared for them. The other one that I've worked on is Tracers ACI. I currently work on this with Stephen Fuselier, and my illegitimate children, Kylie and Dinesh, have been helping me. have been helping me with this as well. They're learning a bit about plasma instrumentation. So this is what I'm normally doing at Southwest Research Institute. I'm developing the optics on these instruments, and then I'm basically the guy putting them through their paces so that we understand how they behave. So when we put them out in space, we know what they're telling us about the environment that they're in. But all work and no play makes Roman a very dull boy. And you've got to do things that kind of allow you to branch out. So like most physicists, I hope, I like to nerd out about things, okay? So one of my first loves was comic books. I love comic books so much, and there was a chance to teach a class called, they were called core classes at St. Mary's. And there are ways to teach people science who don't otherwise want to learn science. So they approached me one day and said, hey, Roman, could we get you to teach one of these classes? I said, sure. I said, what textbook can I use? They said, you can use any textbook you want. And I said, can I use the physics of superheroes? And they said, yes. So I think that class is now going strong for 5 years now. By the way, if you're one of my students and you're here for extra credit, I'm not going to take your name down. Make sure you email to me my favorite anime, which is Neon Genesis Evangelion. Make sure you do that. I also love anime. I have been watching anime since I was 8 years old. 8 years old. There was something called Battle of the Planets here in San Antonio. They would show that on the local stations. And I would watch that just without fail. And again, that was my first love affair with that type of animation. Yeah, there you go. You better be awake. So, and kind of approaching the same, going with the same approach that I had for the physics of superheroes, I said, well, this could work with anime, and I love attending anime conventions. So I went and I pitched that panel, and I've delivered it to San Japan 4 times. I went to Anime Matsuri once. I went to Anime Expo once, and I'm actually going back this year. That's the biggest anime convention in the continental United States. I think 130,000 people showed up last time, and my panel filled up. 317 people showed up, and they had to turn people away. So maybe we'll do better this year. Who knows? So what are we going to talk about today? We're going to talk about Einstein's theory of special relativity. It's one of my faves. And we're going to be talking about quantum mechanics. Now, the premise here is if you allow for certain miracles to occur in these animation shows, are the physics explained correctly? That's the question that we need to answer here. So, is it far-fetched to think that anime can accurately describe scientific phenomenon? It's not. So 2 anime that are actually really good is Cells at Work. So Cells at Work, it's an excellent example of anthropomorphizing the functions of the human body. And I honestly think that you could use this to teach kids about biology, except for those freaking neutrophils. They're like some of the most violent things. They just destroy everything. They knife things, okay? So we don't want to have that with maybe preschool kids, but maybe high school kids, maybe middle school. Another one that is really good is Dr. Stone. I actually learned something from this anime. Does anyone know what, and you can say it. Audience participation is appreciated, but does anyone know what Edison used as his first filament in a light bulb? It was carbon paper. It was carbon paper. I didn't know that. And sure enough, during the anime, Senku actually uses a piece of charred bamboo, which is carbon. So that was the first thing that Edison used, and I didn't realize that until I watched the anime. Go figure. So you can learn something. Just start watching anime. All right, so that's not what we're talking about, you jerk. Absolutely right. We're not talking about anime that are specifically designed to address scientific phenomenon. And so you have to kind of branch out. And so one of the genres that you can look for with this type of animation is science fiction. So again, using this premise that if you allow for certain miracles, like massive objects being able to approach the speed of light, the question is, are those principles represented correctly? Okay, so if you do allow for those miracles, you can accurately explain the effects of traveling at or near the speed of light, explain the consequences of time travel and quantum mechanics simultaneously. Too bad you're not at the full version, because then I could talk about Akira, which is a watershed moment in animation. That anime right there kind of showed the world that cartoons aren't always for kids. And I remember seeing this in 1988 in the movie theater. Yes, I'm that old. And also how subs can hunt like sharks. So if you're interested in these, show up to San Japan this year. Okay, so the first anime that I will talk about is called Gunbuster Aim for the Top. This is the directorial debut of Hideaki Anno. So if any of you were wondering how to spell Neon Genesis Evangelion, it's right there. So go ahead and take a picture of it, perhaps. It ran from 7 October 1988 to 7 July 1989. And you'll find this with a lot of Japanese anime. There's this common theme. We're under attack by some alien force. In this case, they're a bunch of insectoid aliens. And the protagonist, Noriko Takaya, through a lot of hardships, she becomes this pilot of this ultra-powerful robot that can actually take out entire armadas of alien spaceships. But first, she has to learn her science. And the science that she has to learn here is relativity and cosmology. So, I really loved this, okay? At the end of each of these animated episodes, yeah, you can go ahead and take that one. They have these science lessons. Now, some of them are like completely off base, right? You know, they're talking about objects that are moving faster than the speed of light. But some of them actually adhere to scientific principles that we are familiar with. So I'm not going to show the video on this one. I'll show the next one. But in this particular science lesson, Noriko mentions something about space being an ether field. We know that that's wrong, right? The Michelson-Morley experiment showed that that was incorrect. And I want you to understand this, okay? I was watching this when I was like 18 or 19. So I got my PhD in astrophysics from Rice. But the first time I heard about the cosmic microwave background was this. That space is approximately 3 degrees Kelvin, okay? Another thing she talks about in this video, so Newton and Einstein are like passé. There's this new guy, Tannhauser, who won the Nobel Prize 5 times. I mean, that's like freaking awesome. You know, I think the going rate for the Nobel Prize these days is something like $6 million or something like that, maybe a little bit more, and you don't have to put it into research, so, you know, you do whatever you want with it. So, you know, hey, maybe we need to get to working. All right, so space is not absolute zero. So last time I checked, about 13.8 billion years ago, an event occurred called the Big Bang. And that, of course, you know, time, space, matter, energy, all of these things come into being at that point. Early in the universe, you know, right after the Big Bang, it's heavily radiation dominated. You've got gamma rays flying all over the place. Material is not existing yet, but as space expands and things cool down, you're able to form matter, but you still have those leftover photons. And so those photons get frozen into space, and as space is expanding, what was originally a gamma ray ends up becoming an infrared photon, and eventually a microwave, and that's exactly what we see going on here. This is the Kobe observations. So again, Penzias and Wilson won the Nobel Prize back in 1978, and of course Noriko knows this, so she's obviously doing her homework. But we are talking about light speed. Here, would you go ahead and play this? And this is still active, right? Yeah, so by the way, the equations in this video are all correct. I checked. Uh-oh. Maybe, oh, here it goes. Okay. There's subtitles, too. Oh, whoops. can't tell. It's probably just not playing, right? Oh. That's right. Well, I should have asked earlier if videos were going to be okay to have in the presentation. There we go. Stop. There we go. Okay, so lesson today is about the world of light speed. And then she says, okay, we're talking about warp. It's like, no, we're not talking C+. Okay, so they're going to discuss warp in another lesson, unfortunately. So, we'll have to wait for that one later. So while they're going through this, I want you to notice, so there's this one coach that like just pops into existence or just pops out, and he looks like a huge chibi character. And again, he just pops out of nowhere. And I have these students who sometimes like to look at their phones while they're in class, and I always wish I could like just pop up behind them like that. That would be so much great. So while they're talking about this, we'll go through here. So, Einstein, there it is. That's exactly what I'm talking about. I need to somehow, perfect that skill. So Einstein's postulates, this is what they're talking about here. So Einstein's postulates, the laws of physics are invariant, identical in all non-accelerated reference frames to the speed of light in a vacuum. It's the same for all observers, regardless of the motion of the light source or the observer. So one effect of Einstein's relativity is something called energy-mass equivalence. And, if you ask the average Joe on the street what Einstein's theory of relativity is, they'll probably say E equals mc squared. And you know what? They're wrong. That's an effect. It's not Einstein's theory of relativity. And actually, they're also wrong because it's not E equals mc squared, it's E squared c squared. E squared is equal to P squared c squared plus m squared c to the fourth. Okay? You have your rest energy and you have your kinetic energy. And this is the game that we play at the Large Hadron Collider. When we're trying to make more massive particles, we take these things up to as close to the speed of light as we can, and then the scientific term is we smish them together. You smish them as much as you possibly can, and then you try to see if you can make a more massive particle. That's exactly what they did when they were trying to find the Higgs boson, and that's the challenge going on right now, right? We need to make a more powerful collider so that we can try to see if we can make more massive particles. I mean, right now, we're kind of at a deadlock with particle physics right now. So, all right. So, examples of relativity in Gunbuster. So, example one: Noriko's father is lost on a spaceship. So she was trying to follow in Dad's footsteps. So her dad's ship gets lost, and she actually encounters him later. And actually, the delay, I think, what is it? He was gone for 7 years, but for him, it's only been 2 days. Okay. Example two: a 12-second delay during a mission results in a passage of 6 months on Earth. Now, how do these examples work out? Let's talk more about moving at the speed of light, or close to the speed of light. So, how is this constancy of the speed of light possible? Well, Einstein postulated these two effects. One, clocks slow down, time dilation. Things appear shorter, length contraction. So, if you are moving at an appreciable speed, your clock ticks slower. And the faster you go, the way we look at it here in this cone representation is basically we never get fast enough to move off this time axis. We're basically living there our entire lives. If you could somehow increase your speed to a significant amount, you would stop moving so much through time and move more through space. And if you're moving at the speed of light, that's this outer portion of the cone. So again, if you're asking me, well, does that mean if I'm speeding in my car that I'm actually aging at a slower rate? The answer is yes. But I think if you use that excuse with the San Antonio Police Department, they're not going to let you get away with it. So again, typically we're moving through more time than space. Again, the faster you go, the more space and less time you move through. Again, the maximum speed is the speed of light. That is the speed at which information travels. So, are the physics correct? Okay, again, assuming some miracles. Okay, the faster an object is moving, the slower it experiences time. So example 1, Noriko encounters her father on the bridge of the Lucian. 7 years have passed by for her, but only 2 days have passed by for her father. In that case, and if you go and you throw it in those correct equations that we saw in the video, hopefully they were correct, you end up with her moving, or with the Lucian, her father's ship, moving at 0.9996 C. Example 2, a 12-second delay results in the passage of 6 months on Earth. She's moving basically at the speed of light. And again, I'm not saying that these things are exactly correct, but I think what's important is the fact that they paid attention to it, right? The fact that they paid attention to the science, and I think that speaks volumes for the creators. All right, the next one. So, has anyone seen this one? Has anyone ever seen Steins Gate? Okay, Steins Gate's an amazing anime, but you start off one way, and all of a sudden it just takes this U-turn, and you're like, how in the hell did I get on this? And how can't I get off? What's that, Kylie? Yeah, exactly. And you're like, wait a minute, how do I get off this ship? This is crazy. So, again, it's adopted from a visual novel of the same name. It follows Rintaro Okabe, this guy here. Actually, the real brains of the outfit is this character right here. Now, during the passage of the show, they find ways to send these D texts, these dimensional texts, backwards in time. And so even though they can't travel backwards in time, they send messages backwards in time, and they are able to affect their present. And in doing so, they inadvertently attract the attention of CERN. I guess they're based on CERN. So it was really funny. When I was making my transition from dark matter physics to plasma physics, I could have gone 2 places. I could have either come here to Southwest Research Institute, or I could have gone and worked at CERN at the Large Hadron Collider. And I love working at Southwest Research, but I think if I had watched this before, the idea of working for an evil organization would have been great. Because I've always been more of a Sith than a Jedi. I gotta admit. Oh yeah. All right. All right. So first off, the scientific community at large believes that backwards time travel is highly unlikely. I'm not saying it's completely out, but there is this violation of causality. Okay, again, I just said that information is transmitted at the speed of light. Quantum entanglement, though, seems to be somewhat problematic. It does violate those issues. Now, forward time travel, sure. Okay, just fly near light speed. Actually, and I always advise my students of this when I'm teaching this portion of my class in my astronomy class, if you, especially with tax time coming up, it would be really good to kind of just park outside of a black hole. Because, if you were there for a year, 1,000 years basically would pass by on Earth. So, and maybe the IRS would be gone. But more than likely not, and you just, end up owing 1,000 years of back taxes. Now, snippets of the community do think that traversable wormholes may provide a means of time travel. I highly recommend, if you're interested in this, anybody watch Veritasium? Yeah, the latest episode was really, really good. Yeah, so watch that one. He has an excellent explanation of that. But in any case, the jury is still out. So, multiple world lines. Okay, for real? Is this a real representation of a scientific theory? Well, during the course of the story in this particular anime, there's one character who is actually quite beloved, but she keeps dying. Okay, and the main character, Rintaro Okabe, does not want her to die. But it seems that as long as she's in this one world line, she is destined to die. So his solution is, well, we've got to somehow switch world lines. And of course, this convoluted map here is showing you all the little jumps and leaps that are going on here. Now, again, this is just, a division of fate. Somehow or another, you have, and this is almost kind of like the way Marvel Comics represents their universe. When you get to a point, you can go one way or the other, right? You come to some fork in the road. What defines which universe you are in is the outcome. And it's interesting. That could work for us as well, right? You could have parallel universes where something else happened. It's kind of funny to think that there's maybe another universe where me, the person, is still married to my evil ex number 2. That poor bastard. So again, the question is whether or not multiple world lines is a valid scientific concept. Well, quantum mechanics is pesky, okay? Quantum mechanics accurately explains the behavior of things like electrons, photons, or atoms, but it's a pain in the butt because it never gives you a straight answer. It kind of gives you the whole roundabout thing. And again, a very good example of this is the Schrodinger's cat experiment, and it's a thought experiment. Don't think about doing it, okay? If you do so, you're a horrible human being. But if you've never heard the setup, you've got this box, you put a cat in there, you put a vial of prussic acid or something that can rupture, and then you have a decaying source. And then you close the box, and then you ask the question, is the cat alive or dead? Well, the answer in quantum mechanics is both of those states are equally viable. But if you want to know what the outcome is, you open the box, and then you destroy the experiment. So how do you rationalize that? Again, if you're just going with straight quantum mechanics, that's not really an answer. But if you use multiple world lines, well, then you have to figure out which universe you're in. And so you open the box. Now, granted, in that case, that means that if the cat is alive, you've still killed the cat in another universe. So don't do that experiment. That's a horrible thing to do. All right. So the upshot. Again, the cat experiment is a commentary on the... Isn't that great? I love it. You did notice a shirt, right? So again, the whole idea is that before you make that measurement, before you destroy the experiment, you have a system with all these possibilities. Okay, they're all equally probabilistic. But when a measurement is made, only one of the possibilities occurs, and all the others go to 0. But if you have a many worlds interpretation that resolves this world line break, somehow or another, you've got another universe. Okay, and again, if you think it's crazy, Alan Aspect, French physicist, won the 2022 Nobel Prize, and he is an avid supporter of multiple world lines. So again, it's something that allows us to explain the phenomena that we see, and that's what we do with scientific theories. Okay, that's what we do with scientific theories, and we will keep those theories until we can find one that's better. So, in conclusion, do we watch anime because we're trying to make sense of science? And I sincerely hope not. Because when I was doing my research, my original research was in dark matter search. And after writing my master's thesis, I had to somehow find a way to get these dark matter wave functions out of my brain. I was kind of like demons out. So what did I do? I binge-watched the entire Soul Society arc of Bleach. 60 episodes in one weekend, baby. That's the way I go. No. I stayed on that couch all weekend, Kylie, because that's the way I go. I'm a committed guy. Ask my wife. Now, but I think it's important. It can and does often stimulate the imagination. I mean, I think being a kid and watching Star Wars in 1977 stimulated my imagination. Every time I read a comic book, it stimulated my imagination. And I want to say that in some kind of crazy indirect way, that kind of brought me to where I am now. So with imagination comes questions. Is that even possible? Is that real? And that's really with what all great discoveries start with, is those questions. So thank you very much for indulging an old anime guy, and I appreciate your attention. Oh, and by the way, if any of you have recommendations of anime that I could review, there it is, thephysicsofAnime@gmail.com. Thank you very much.
All right, thank you, Roman. Remember how I said tonight was going to be interesting? That was certainly interesting. No, really, it really was. Let me go back. Let me leave it on the.
What is that?
That's our trivia coming up.
Sorry about that.
It's hello.
Oh, now it's. Oh, I turned it off.
Oh.
It's
Okay.
Old habits die.
The number, we got the TV working, so the number's on the TV now. And I've already got some questions in. The first one is what's your favorite comic book run?
Oh, God. My favorite comic book run? So I really love the Daredevil Born Again series. That was just freaking amazing. Batman Year One, Batman The Dark Knight Returns. It's kind of hard. Favorite superhero? Well, DC, it's Batman, right? Because he's rich and he's awesome. And he could fund his own research, right? Then that's really important. Really important. He's got to, And then on the Marvel side, it's Captain America. Every single day, it's Captain America. When I was a kid, I used to get those galvanized steel trash can lids, and I would practice bouncing those things off of them. I wanted to be Captain America so bad.
The next question is, have you watched Cowboy Bebop?
Oh. Cowboy Bebop is actually a wonderful anime, and yes, I have watched it. And if there's anyone in the room who actually wants to start watching anime and you're like, well, I don't want to watch anything weird like he watches, Cowboy Bebop is actually a really good starter anime. I actually got my wife to watch a few episodes, and she actually liked it. So.
Interesting. I mean, they didn't ask my follow-up is how does that one do on the physics?
It's funny. You don't have anything moving at light speed in Cowboy Bebop. They actually, I would say that they adhere pretty well to physics. I've never really. Yeah, but I need to kind of look into that a little bit more because they're making trips between planets very rapidly, but again, not at relativistic speeds, or maybe slightly relativistic speeds. Speaking of which, has anyone seen the three-body problem yet?
Oh, it's so good.
It is so good, and the physics that are represented in that series are actually well within reach of our current technological levels. So.
This one, I guess, is more of a clarification. Are you going to San Japan?
I am. I always volunteer at San Japan, and I pitched my panel for this next year. I'm just waiting to see if they're going to accept it. I'm trying to do it on a Saturday because they usually either stick me on a Friday afternoon or Saturday morning, and it's really hard for people to get there. So I'm like, hey, man, I've done this like 5 years. I'm ready for prime time, man.
Yeah. So it sounds like stay tuned for that.
Yeah, stay tuned for that. We'll see. Maybe they'll announce it at Anime on Tap. I'm joking.
We talked a lot about physics and the plot of an anime, but what about are there any moments in animation that strike you as particularly inspired by physics and physical principles?
Oh, wow. Well, okay. Not so much in animation, but there's a superhero deconstruction of superhero genre show called The Boys. And there's one part where the Superman analog Homelander, they're trying to get him to stop a plane. And he's like, how can I stop the plane? Because I have no means to. And I thought that was cool. They paid attention to the physics. We see Superman divert the plane. Well, how's he doing that? You can't do it with super strength because you have to have something to push against. You got to have like telekinesis or something like that as well. So I can totally nerd out on this stuff. Ask away.
Someone asked if you've ever seen Your Name, and they say it's a good time travel.
Don't even start. I love that. Your Name broke me, man. That is a great anime, and they did pay attention to the physics of the meteor, right? As it was coming in, and the devastation it would cause. Of course, it's a magical anime, and there's a lot of deviation in that case, but it's still nonetheless a beautiful story. I had actually heard about it when I attended San Japan, and they were talking about it in a Funimation panel, and I said, I'm gonna watch that, and I did, and I bought it. It's just an amazing anime. I highly recommend it.
All right, not really an anime. This is not an anime at all. But in your opinion, how did Interstellar do with these theories?
Interstellar is, I mean, what is it? Kip Thorne was the scientific advisor for that. So, I mean, yeah, everything up to the Tesseract at the end, everything is like dead, spot on. All of the physics represented in that movie are spot on. But again, you don't think so, Jonathan? Okay, we'll talk later offline. But no, I mean, I think on the whole, it was well done. And The Martian is another notable movie as well. So.
All right. There are no further questions, so let's thank our speaker once again.
Thanks, guys. I appreciate it.
All right, now it is time for the favorite part of the night. For those of you that have to go, that have to depart early, thank you for coming. Make sure that you, if you haven't already, that you tip your wait staff very well. They do a great job helping us, as always. And for those of you that can stay, we're doing our trivia, and today's theme is Toon Trivia, where astronomy meets cartoons. So stick around for that. We'll come around with papers, and I'll try to get our pretty photos that you all have sent me on the television screen. We'll take about a 5-ish minute break. Let's say around 8:45. Let's estimate that starting trivia.
Does everybody who wants to play have a trivia sheet and a pen? Okay.
All right. Oh, shoot. This photo comes to us from Ethan. Thank you, Ethan. Very pretty. I wonder how many of you were able to see the prominence. So here's a good view of it in this photo. Now this is Ethan right there. Thank you. A really amazing photo. For those of you that didn't get to see this in its full glory, Ethan went to Maine, right? Is that There's other eclipses. They're not going to be over Texas, but there's a lot of other opportunities. If you make a nice trip out of it, it's worth it.
It's a heck of a trip. Most of them aren't in the U.S.
No, yeah. It's an international trip for sure until 2045. 2045 is the next one here in the States. So,
Ethan, what made you go to Maine? What made you go to
let me,
Maine? Or why'd you pick Maine?
Hold on, let me.
That one's not mine. That's one of my friends from Missouri.
These set of photos. Hello. Oh, nuts. From Lee Childers, how is that? Yes, thank you. This one's very interesting, and once again, there's the prominence down there, the pinkish hue, the pink color. I mentioned this last month, but it comes from hydrogen. So hydrogen glows that pink color because if you look at it through a spectroscope, the lines that dominate are blue and red. So combine blue and red, you get pink. So really sharp photo. Here's another cool one. There you can see the prominences real well. Oh, wow. Really nice job with what do you call it? Time lapse surrounding the center one. This one's also good because you can see the beads, the Bailey's beads there, the last moments of sun over the crevasses and mountains of the moon. And a close-up image here. Very sharp. Thank you, Lee. Let's see. A few more. Yeah, I'm trying to find.
Did anybody experience totality? I know if you're in San Antonio, it was.
Oh well, this one's appropriate because I think it's what most people saw. Is this Brian? Is this yours? Yeah. I thought that was you.
Wah, wah.
What does that mean? See if this.
He's got one more.
It's not working. You know what? Let me. Announcer's prerogative. Oh, there we go. Okay. This is what I got. So it was better than nothing, but as you can see, it was shrouded. But the photo doesn't do it justice because it was so dark, and I really wasn't expecting that. And what I did, and I'm not going to do it now, it'll take too much time, but like I put the two together of the annular eclipse and this one, because the annular eclipse, I also saw it through clouds. So there was a lot of similarities for me personally between the two. And if you look at the sky background, it's so different. And that's really what stands out to me for those two photos and what makes me realize how special the total one was. And the fact that with that one, you're not seeing the sun, you're seeing its corona. Oh, yes, my Colorado hiking photo. All right.
What What 14er was that?
Quandary Peak,
Where's that?
just south of Breckenridge. It's the southern end of the 10-mile range, if anybody knows the 10-mile range.
It's 8:30.
All right. We are ready to get started with trivia.
With more ado,
Cartoon and astronomy. Remember, max group size of 4. Only write the letter of the multiple choice answers, and no cell phones allowed because we want the prizes to be given out fair and square. So let's start with question 1.
question 1. Sailor Moon, in the classic anime Sailor Moon, Usagi Tsukino, who later becomes Sailor Moon, befriends a black cat with what celestial name? Is it A, Sailor Venus, B, Sailor Neptune, C, Luna, D, Aurora, or E, Furball? Personally, I've only seen 2 animes. That's One Punch Man and Neon Genesis Evangelion. Yeah, that's not a me question.
Yeah, that's the closest
No, I've
thing
seen
I've
Avatar,
ever seen.
but I don't know if it counts. I don't know what the definition of anime is.
Wait, are you guys
That-
arguing that Sailor Moon isn't an anime?
No,
No.
Avatar.
Avatar is technically not an anime, but why is it technically not an anime? Because it's American. So anime
Yeah.
is specifically a Japanese.
It's like champagne. You can't call it champagne if it's not from France, specifically the Champagne region of France. Tequila is also like that, by the way. Tequila has to come from tequila in Mexico.
The anime region of Japan.
You can have mezcal. You can have agave. Yeah. You can't call it tequila. All right, let's move on. The Last Astrobender. So perfect timing. In Avatar: The Last Airbender, the Fire Nation. The Fire Nation can be empowered by this comet, which passes Earth every 100 years. Is it A, Sozin's Comet, B, Ozei's Comet, C, this comet, D, Roku's Comet, or E, Kuzan's Comet? What did I say? I said Ozei? Oh. Ozai. Okay.
Too many cultures.
You can't do our man Mark Hamill dirty like that.
Wait, who's Mark Hamill?
Luke Skywalker?
Yeah. Hey, too many actors, okay?
But he's the guy.
It's late. It's late and I'm 4 beers in.
All right. Everybody go down to question 2? All right. Numero 3.
Question.
You have the clicker.
I have the clicker. Question 3. Disney and astronomy. In 1931, Pluto made his first appearance on the big screen in which vintage Mickey Mouse film? Is it A, Man's Best Friend, B, The Moose Hunt, C, Lost in the Woods, D, Mickey and the Seal, or E, Mickey Mouse Clubhouse? Bonus, just write it next to your letter for that question. In what year was Pluto discovered? You get a half point if closest gets a half point.
Pluto the formerly known as Pluto the planet. Now known as Pluto the dwarf planet.
want to go back and watch the original Disney stuff.
This makes me really think Mickey Mouse is old. He's old. Yeah. But he's timeless, so, you know. All right, question 4. Good to move on?
Oh.
Kung Fu Astronomy. In the hit anime Kung Fu Panda, villain Tai Lung is held captive in Korgom Prison, located deep in the Tavan Bog mountain range of what country? A, China, B, Pakistan, C, Nepal, D, Mongolia, E, Japan. P.S. This mountain range does exist, but not the prison.
Is there contention with whether Kung Fu Panda is an anime? Hey, you talk to Sam.
Okay, in the hit animated movie, there we go. You can't argue with that one.
Animated.
Listen, it's got Jack Black is a panda. It can be whatever it wants to be. Skadoosh.
Skadoosh. Man, I haven't seen Kung Fu Panda in so long. All right, everybody good? Question 5. In the Gravity Falls episode Little Gift Shop of Horrors, famous astrophysicist Neil deGrasse Tyson voices the smart version of which simple character? Is it A, Grunkle Stand, B, Dipper Pines, C, Barack Yamama, D, Sheriff Blubbs, or E, Waddles?
Waddles, I love Waddles. Waddles the pig.
I'm excited for trivia to become like, what can we get them to say?
I think was played by the voice actress of the girl. I think was the same voice actress as Louise from
Everybody good?
Question 6. The One Piece Israel. In the popular manga One Piece, Enel, which one was right? Enel travels to an ancient city called Berka, located on which celestial body? Is it A, Mars, B, the Moon, C, Ceres, D, Planet 9, or E, Earth?
Any believers in Planet 9?
Is One Piece the one that they made a live action recently? On Netflix? Okay. Thousands, I think. Okay.
Does anybody need any questions repeated?
It's too many, that's for sure.
Everybody good on question 6?
We're good for the bonus.
All right. Bonus. Below is the list of the top 5 highest grossing anime films, according to Sam. Reorganize them from highest grossing to lowest grossing. List only the numbers, please. You have 1, Spirited Away, 2, The Boy and the Heron, 3, Suzume, 4, Demon Slayer, Mugen Train. Mugen Train, 5, Your Name. So, highest grossing to lowest grossing, numbers only, please.